So I'd like to welcome everyone to this month's ReproNim webinar. We are pleased to have our own Sebastian Urchs talking with us about sample level metadata integration and search. Sebastian got his PhD a few years back ago at McGill using image-driven sample stratification for autism and prediction of diagnosis work. And as we were talking about before, someday I would kind of love to hear some of that, as well. So we look forward to that. But Sebastian works in JB Pauline's lab. JB, as many of you know, is our leader of our training core and a key member of all sorts of different aspects of things that we do. JB's lab apparently is Origami, which is a lab dedicated to image analysis and other things that I don't even know about. But without further ado, I will turn things over to Sebastian.
Yeah, thanks a lot for having me. And today I'm going to talk a little bit about work we've been doing over the last couple of months in the lab, the Origami lab. And this is work that we've been doing together with Jonathan Armoza, who is the front-end developer, Nikhil, who's a postdoc in JB's lab, JB, of course, and then also Vincent, who is a postdoc working on Parkinson's data. And so the first thing I want to mention is why sample level search. At the MNI and in our lab, even, we have a number of use cases of people who are looking for data or for ways to define cohorts. And so one example is a third postdoc, actually, Jerome Dacus in our lab, who's working on something called dataset shift, which is when in a machine learning context, your training and test data are shifted with regard to some covariate of interest, for example, age, which is often the case. And so he's investigating how this type of shift impacts prediction outcomes, and also what mitigation strategies might exist there. And so some of the questions he's asking is, what is the impact of training on shifted data versus testing on shifted data? And so for him, it's very useful if we can find data with certain characteristics at the cohort level. And then he uses this to do analyses and looking at what a shift in the training sample causes on the prediction side in terms of prediction performance. And so another use case that we have locally here is our open data consortia, where a number of researchers get together, already have some data, for example, on Parkinson's, and then are looking for other open data sets that are not at McGill to augment this, or for researchers to collaborate with. And again, that's a cohort level question where you're asking about diagnosis and specific assessment tools and other demographic variables maybe. And then the third case that we have encountered is the case of an actual clinical institute. I also work at the Douglas Mental Research Institute, Mental Health Research Institute, and clinical consortia. And what they share is sometimes the question of what data do we actually have. And often this is the case because the PIs own the data, and the data may not necessarily be organized in a systematic way, or the information about the data may not be exposed in a systematic way. So sometimes it's hard for the institute or the consortium itself to be aware of the exact amount of data and type of data that's available. And there is another challenge about this, which is, as an institute or a consortium, you may be interested to tell the world that you have certain data available, even though it's not open. So the world or other researchers can make an informed decision on whether it's worth it to go through your data usage agreement or other processes you need to complete in order to gain access. And so how can you do this without exposing the data? So what all these three use cases here have in common, that you want to ask questions about the sample or file level. And that's kind of what this talk is about. How can we get there? One question is, what level of detail do you need for these types of questions? And this is not an official taxonomy of details, but I find it helpful. At the bottom, you have files. And so if you need to run an analysis, you need to know what the file format is. So if it's in bids, you can use bids apps, for example. But slightly above that, if you want to ask questions like cohorts and individuals, you need to have file level or sample level metadata. And so that's not the data itself, but just descriptions of the data, like this imaging file is about a person with schizophrenia, and it is of type MRI, for example. And then the highest level and what is often used to find data sets is just aggregate metadata for an entire collection of data sets. So, for example, named data sets like abide, we could describe it at that level. But so what we're looking for the purposes of core definition is sample level metadata. And so when we're asking, well, where are all the metadata? Then the answer is they're in a lot of different places. So often people are now uploading the data to data repositories or data curation centers like Dandy, OpenNeuro, eBrains in Europe is another one of these. And these curation centers have often the actual data, not all of them do. So for example, CMP is a metadata repository where the data is not necessarily hosted on the same platform, but they also have metadata about the data that they have. And so this is at different levels of details, for example, data set versus sample level, using different metadata models and different formats. And what informs these metadata models and the level of detail is often what the data curation center itself is trying to do with them. And so there's often a way to search them, and there's often a way to run analyses directly from the platform. And that's what these models are tailored for, but they're not the same, basically. And so if we want to search across them, we need to find some way of integrating these different representations of metadata, again, at the sample level, while we're leaving the data where they are. So data should not be moved for various reasons. And so what we're adding to our little suitcase of requirements here is that it has to be cross data set, not just sample level. Okay, so the question that we asked a while ago is, well, basically, where is this working successfully and at scale, or like in a big context? And there are two examples that stand out that I thought was interesting to briefly talk about. One is for observational healthcare data. It's called the Observational Medical Outcomes Partnership, or now it has a slightly different name. And the other one is for web search, or Schema.org. And so what I want to do is briefly introduce both of these examples, and then to show how we can take some lessons learned, so to say, from what worked and didn't work for them, and try to inform our own decisions about this problem. And so the OMOP origin story I find is very interesting. Basically, Merck is a pharmaceutical company, and they had a painkiller drug, and it was approved. It went through drug trials and was on the market. And people found out that it leads to an increase in stroke risk. And so that sometimes happens. The problem here was that Merck was alleged to have known about this and not acted. So people got injured, people died, and this drug was still on the market. And so two things happened. People sued Merck, and Merck settled this lawsuit for a large amount of money. But for us, the more consequential thing was that the United States Congress said, well, that's not good. Let's have a hearing about this. And they did, and they asked the FDA, who's responsible for figuring these things out, why didn't you find this out before we eventually found out, I guess. And so the FDA said, the problem is that we don't have enough data. Drug trials aren't long enough, and we cannot run them long enough to find these low incidence rate problems. And the people who have these data, like hospitals and insurance companies, we don't have their data. We don't have a way of accessing this. And so Congress did what Congress can do, which is pass a law and said, well, do this now. And so this is how the Observational Medical Outcomes Partnership came about. And the reason this is called a partnership is because the FDA worked on this together with 17 pharmaceutical companies and the pharma lobby, which ironically has as its abbreviation pharma. Or I guess it's not right. So what they did is try to solve this problem. You have many different places where this data already exists, hospitals, insurance companies, doctors' offices, and you kind of have to bring it together. And so the thing that they, over many meetings and a long development process, came up with is called the OMOP Common Data Model, or OMOP CDM. And so this is supposed to be a holistic view of observational events in a patient-clinician interaction. So things that can happen to a patient, essentially, like being diagnosed, being given a drug, having a certain side effect, and all these types of things. And the idea behind this was that all of these data sources will represent their data in this format so we can then consume it in a single place. And so one takeaway here is that this is a person-centric model. So person is the thing that we're asking questions about. So that's what the model has at its core. And then the other important thing here is that they made a decision to reuse existing vocabulary. So the terminology with which these values are annotated here are used consistently, and OMOP makes very specific prescriptions about what data vocabularies to use. So this is what this workflow looks like. You have different data sources. They're all represented in their local databases. There's a transformation. You end up with the OMOP common data model, and then you can run analyses on them and look at analysis results. And this is how you can get the sample sizes required to find these rare events. Now, the vocabulary is very interesting because OMOP actually uses large existing vocabularies for different domains. And so, for example, if you're making statements in OMOP about a clinical diagnosis, then you don't have a choice but to use the SNOMED-CT or clinical terms vocabulary. And SNOMED-CT is a widely used ontology or hierarchical vocabulary that's been in development for many decades, and essentially represents the linkage between different clinical concepts, but in the case of OMOP, specifically diagnoses. And so if we're looking at Parkinson's disease, we can see that it's a child of cerebral degeneration and Parkinsonism and so on. And this is very helpful because we can now all refer to this vocabulary when we're talking about diagnoses. So all of the different diagnostic manuals that are used in different places now have to map into SNOMED. And so if we're asking about the diagnosis of a person, we can have the same term for the same diagnosis. And there are other such vocabularies for other aspects of the model, like RX norm for drugs and so on. So when they were done, OMOP ended, and with it, the involvement of the FDA and the pharma industry. And the important thing here is that all of this infrastructure that was built up was handed over to the OHDSI, which is an academic organization hosted at Columbia University. And this is the state of OMOP today, where it's mostly a research project, and it has collaborators all across the globe, and a really impressively large number of data points that are integrated in the system. So these are some numbers, I think, from last year, where they have 600 million unique patients and several billion of unique data points and so on. And now the question you can ask is, well, what can you do with it? Well, you can do the type of research that was the intentional goal of OMOP. So, for example, this is a very recent paper on COVID vaccine safety. So there, when the vaccines came out, there were a number of questions about side effects. And I mean, I don't want to go into too much detail. This, I think, is the main point here. They were able to run this question on a sample size of 126 million people who were observed at a time before COVID hit. So you could get an accurate measure of the background incidence rate of certain side effects, and then compare them to the people who were exposed to the vaccines. And so this is a very helpful thing to be able to do, obviously. Now, the second thing I want to talk about is Schema.org, and I'm going to give a very brief, I hope as brief as possible, introduction to kind of where this is coming from historically. So if we're looking at the internet, before it existed, documents were on computers, and you had to know which one in order to find them. So the big innovation here was, let's create links between documents through the HTTP protocol, and now we no longer need to worry about where these documents live, because we can just click on hyperlinks and navigate between documents that live on different computers. And so this is Tim Berners-Lee, who famously proposed that idea. Then people figured out that this is a very useful thing to do, and services start evolving where you can actually start adding information yourself and participate in the internet. And that's kind of what we refer to as Web 2.0 sometimes. And so the problem now started being that they're not just documents in the world, they're also facts, and facts can be different in different places. So for example, if Ernie and Barrett are friends on MySpace, but not on Facebook, which is true. And in order to overcome this, again, Tim Berners-Lee had the idea, well, now let's link facts and not documents. And so what that means is that rather than looking at the fact where the information is stored, we just try to make the information itself semantically understandable and readable for a machine, so we can ask questions to a computer like, is Ernie a friend of Bert? And so this is the challenge. We need to make sure that the machine can understand what that means. And the framework for this is the RDF, or Resource Description Framework, which is a standard of the W3C. And very simply speaking, what it tries to do is to take statements and organize them as a subject, predicate, object. So kind of like we speak as humans. So if you take Ernie as a friend of Bert, then we would have Ernie as a subject, is a friend of, as a predicate, and Bert as an object. And because there are three things, we call them RDF triples. So what you can do with these statements is make statements about things in the world. So Bob is a friend of Alice, is a person, is born on a certain date. But you can also make statements about the same resource from different locations, and now you start building a graph. And this is why we're calling this also a graph data model, where we can link the information that different entities are aware of about things in the world, and then have something called linked open data. And so this is very useful, obviously, for data integration. This was kind of the vision behind the semantic web. However, the question is often like, what does it mean to be a friend of? And all of these relationships have to, again, follow a vocabulary like we've seen in the OMOP case. And so the reality on the internet is that there have been a lot of these vocabularies or ontologies, and it's hard to keep them all synced up, essentially. So this is the situation that Schema.org encountered, basically. So the problem for Schema.org was that search engines are all competing with each other, and they needed to offer their users something more interesting than what they were giving them before, which was contextual information for the search results. And they wanted to do this by reading structured data, or the type of information that linked open data might be providing, and then adding this to the search results. So if you search for Montreal, you see pictures of Montreal, and you read a Wikipedia article about it on the side, and what you've probably already seen on the search engines. The problem was that although these formats and standards existed, there were a lot of different vocabularies, as I just said, and so the webmasters and the people who were adding this information to their websites really often didn't know what exactly to do, because Google used a different vocabulary than Microsoft, and different things like events and recipes needed different ones. And so there was essentially a type of chaos. And what these search engines did is said, okay, let's get together, let's figure out a way to bring some order into this, and let's try to make a consistent vocabulary for the types of things that we're interested in the world, but keep it really simple. And so this is what Schema.org became. So it's again a taxonomy of terms. So there's hierarchical relationships, but really compared to what OMOP did, it started very simple. I think there were maybe 10 domains in the beginning about things that the search engines cared about, like events and recipes and such things that are helpful to integrate. And they kept it purposefully very minimal, in order to make it easy for webmasters to annotate the data and to use it. And one of the specific design decisions that they made is to put the burden of data organization harmonization with the consumers, which are the search engines themselves and big international companies that have the resources to harmonize messy data, essentially. So if somebody gives you information in schema.org and it's not exactly about the same entity, and there's not a URL to identify it as the same thing, then Google and Yahoo say, we can figure this out. Let's get the data first. Obviously simplifying a lot here. And so now, in order to do something useful with it, they do have to harmonize it. They do that on their end. And so when they do this, this is something called, for example, the Google Knowledge Graph, which is the structured data of the web crawled together and then organized into a graph representation that is internally well structured and of high quality, and that they use to serve these contextual clues here in the search engine. The other thing that they're doing, which is probably many of you are already familiar with, is using this to find data sets on the web, however, not at the sample level, and also with relatively basic metadata, but this is something called the Google Dataset Search, which is based on the same type of structural annotations. And so based on these two examples, we were trying to figure out, okay, well, what can we learn from this, essentially? And I think one thing is pretty clear. We don't have the types of resources and institutional backing necessarily that these two examples have. So there's no law that was passed to do this, or there are no multinational corporations involved in this. So obviously there's a difference in scale, but there are also some similarities. So one thing that stands out about OMOP is that it's a research product, essentially. It's about public health and safety research. So the consumers are researchers, and it is designed around making data easy to consume for researchers. It's maintained by a community, and now that it is actually an academic institution, there aren't that many resources to do the data harmonization. So the OMOP process really requires the people who are providing the data to harmonize them according to the protocol. So to bring them into, for example, mapping with SNOMED. And on the Schema.org side, similarities are we're really not in the same situation as OMOP in terms of the people who are bringing the data in. So we're not talking to hospitals and insurance companies who already have very structured data and are paying a lot of money to ensure quality, but we're talking to mostly individual researchers through the data curation centers. So data is heterogeneous, and it's important to make it very easy to use these tools. And so one thing that is the Schema.org has done purposefully for this is to go very iteratively with complexity. So to start very simple, and then as adoption increases, to add complexity to their metadata representations. And it is also a community maintained initiative. So with this short background in mind, these were kind of our takeaways of how can we approach this. So the first takeaway is you need a really concrete use case that people care about. So OMOP had drug safety, and there was a law. People are really on board. Schema.org, these search engines really needed this, and web scale structured data is an appealing incentive. So you need to find something that is really that people care about, and then you can bring people together who care about this. The other takeaway was to make it really simple. So to really not front load complexity, to just make it initially as simple as you need to pass your use case, and then think about adding complexity later. To reuse as much as possible. So OMOP did not go, even with all their money and infrastructure, did not go about developing new vocabularies, but rather reuse things that were developed in the community. And this is useful now because they don't have to maintain SNOMED and all these other things, but they keep using these vocabularies. However, they're also consistent about which ones are being used to make it easy for researchers. Make it easy. So Schema.org, there were a number of tools and integrations with web publishing platforms, and they even went so far as to say there's a single vocabulary. For OMOP, there's a clear guidance on how to structure your data before you join the OMOP organization. And then an iterative development. So this is more true of Schema.org, I think, than OMOP, but essentially, again, start small, add complexity later. And OMOP also has a process of expanding their data model as more use cases are being integrated. And the last point that is really important is, even though there was so much firepower behind these initiatives initially, they're both community maintained. And I think this is really an important aspect that is important to keep in mind. These are collaborative efforts, effectively. So based on this, we were trying to approach the original problem that we found of the use cases of the people who we work with, essentially. And so as our concrete use case, we picked the ability to define a clinical cohort with neuroimaging data. And because we have people at our institute who are working with Parkinson data, we further constrain and say, okay, well, let's do this for Parkinson data first. And there is the Quebec Parkinson Network that is imaging is acquired locally at the MNI. And there's also the PPMI initiative that some of the researchers involved in this are part of. And then there are the open neuro open data sets, which are not targeted to Parkinson's, but which we thought would be really interesting to also integrate into this in order to answer some of these questions, like what other open data sets are out there that fit criteria that researchers are interested in. Now, the next takeaway would make it simple. So we thought, okay, let's just look at the minimum amount of information that at the moment we care about. So let's say imaging modality, and then just age, gender, diagnosis, and what assessment tools are available for each person. And just go with this, even though we know that there's more available, and we will eventually be interested in other things too. And comes a point of reuse. So this, I think, is really where the community aspect is very important, because everything we're doing here was reusing things that have been built in the neuroimaging community, and to a large extent actually in the ReproNim community. So all of our input data was structured in BIDs. Open Neuro was already annotated by Dave Keeter into the NIDM data model, which is a graph data model, also at the sample level. And so we reuse these annotations for getting information about the imaging modalities. And then reusing existing processes, map them into the NIDM terms vocabulary that is a standard vocabulary for imaging related terms. For age and gender, we used the BIDS-like terminology for the literal values, and try to make them consistent with what BIDS does in its specifications. And then for the diagnosis, we used SNOMED-CD because that's widely used diagnostic vocabulary. And for the assessment tools, we decided to use ReproSchema, which is another initiative that is trying to build a vocabulary, but it's really more than that, for assessment tools that describes really down to the item level how neuropsychological tools are made up and then computes aggregate scores. So for us, the important part was to have a consistent namespace for the tools that we're encountering, so we could make sure that if it's MoCA in one data set, it's MoCA in the other data set. Okay, and so what have we done specifically for this metadata integration aspect? So the data that we encountered in these different data sets, so whether they be Open Neuro or PPMI and KPN, were generally harmonized on the imaging data. And that is, as I said, thanks to the work from IDM and Dave Keeter. But on the observational metadata, or it's often like tables and spreadsheets, there was really a high level of heterogeneity. And although NIDM does annotate concepts for these columns, we really wanted to go down to the value level, so where we can really understand what each individual value means. And so for this, we needed to first figure out what does each of these columns refer to. So which of the columns in the spreadsheet is about age, which is about gender, which is or are often multiple about diagnosis and assessment tools and so on. And then, as you can see here, these values are not always intuitive or consistent. So the next step was to find a way to harmonize them into these existing vocabularies or existing specifications that I've shown on the previous slide. So very generally speaking, the first question was, where is the information? And the second question was, what information is it? And so now we're coming back to the idea of the linked data or RDF triples, because where we chose to put this information that we had just harmonized is essentially the 90M graph. And now, if you have not been familiar with the 90M graph, it's a graph representation of data elements. File level metadata. But as I said before, we had a more restricted view of what clarity we wanted for our values. So we really wanted to make sure that there is harmonization at the value level and that we're mapped to the same vocabulary. So essentially what we did is the 90M has this subject level node, and we decided to take all of this harmonized data and add it onto this node. So this is kind of a zoomed in view of our very simplistic data model linked to the 90M graph. And so for the imaging modality, as I've mentioned before, we took this information directly from the 90M graph, where it is fully harmonized with the 90M terms vocabulary. And then we went and took these concept level annotations of the 90M data elements and try to figure out, well, what are they about, and what do their values actually mean, and then harmonize these values according to vocabularies and specifications, and then stuck them in here. And so this has been an automatic process to some extent, but also a somewhat manual process. So now we're getting to the point of, well, make this easier, right? Because the way we've done this for the first demonstration was reusing a lot of existing information, but not necessarily something that can scale easily or be easily repeatable. And so one thing that we wanted to do is try and find a way of asking these questions in a clickable interface way. And so I have a brief demo for this for an annotation tool. So essentially, this I just want to caveat this by saying this is an extremely early mock-up, so this is not meant to go out to anybody in public, other than through this talk, I guess. But what we've done here is we loaded a bits CSV file and the corresponding data dictionary, and then we can go and take the data dictionary to annotate. I mean, to just make a description of what these columns are for a human annotator to remember. And then what we want the participant to eventually be able to do is just go and tell us where the information is, right? And so this is not very interesting if there's only one column, but if you have something like diagnosis and there are multiple columns, this is actually maybe easier than doing this one by one. And so once we've done this and we've done the classification, then eventually, and this is really just a screenshot, we want people to be able to tell us what the values are about. So this is an example for what a sex annotation page could look like, where we find a number of raw values and we use the data dictionary to remap them to something that is more string-like, and then we have some guess of what it is, but really we want to make sure that the user has some ability to tell us if we guessed right. The important thing here is that we don't accept any value for this, but really, could I zoom in a little? Yes. Does that help? I just saw a comment in there. I mean, this, you know, just an example view, essentially. Yeah. Okay. So I'm gonna jump back into my presentation. Okay. So with this in mind as a way to make it easier as an annotation tool, and something that I think would also be a great way to collaborate with some of the other metadata formats in the ReproNim world. So with this in mind, here is essentially the way we've tried to implement this. So to get a very simple first prototype working, we took, now this is kind of our data model and the 90M graph blanked out to make this easier to see. But we essentially took the representations that were harmonized, stuck them in such a graph data model. And this is running on the Stardock triple store and on a Compute Canada instance. And really, on top of all of this integrated and harmonized metadata, we wanted to have a tool that can run these questions that we originally had of defining cohorts. And so the way this would work is that because we have multiple individuals that are linked to, for example, Parkinson's disease as an entity, we could make these links between two data sets that share individuals with certain characteristics that have Parkinson's disease. And this is going to be my second demonstration. So this one is actually a little more mature. So should I zoom into this one? Maybe like that. Yeah, okay. So on the left, you see a number of fields for you might recognize here the different domains that we said we care about. So there's age, gender, modality, and diagnosis. And if I just hit query, then we will see all of the data that this graph is currently aware of. And so most of them are from OpenEuro, the 200 data sets and 10,000 subjects. And I can prove to you that we're actually looking at subjects, because if I constrain the age, then there are fewer subjects. But what's really interesting is that we have these diagnostic terms here, which are from the SNOMED CT vocabulary. So if I go in and I search for Parkinson's disease, now I only get subjects that actually have an asserted Parkinson's diagnosis. So not just the data sets that contain them. So if I take out the age, we see that there are about 1,000. And some of them are, yeah, so here's PPMI and QPN. And then one thing we've done specifically for Parkinson has been to add not only the name of the assessment tools that are available for them, but also going down to the value level. So, for example, if I say, okay, I want the MoCA, I want individuals with a MoCA score, upper bound should be 25, then I can enter this like that, and again, find a list of individuals. And what you can eventually do with this is say, okay, I'm interested in some of them, checkbox it, and then download results. Download results, I think, is something that we'll talk a little bit more about in the future, because at the moment we can choose to actually expose the metadata that we have, but what would be much more interesting would be to really point people to where the data are through something like Data Lab. Okay, so this has been the core tool. And so my last slide is going to be talking a little bit of how we already and plan to interact with the community. And I think the takeaway message here is as much as possible and already to a great extent. So we're using already the 90M annotations from Dave Keeter, and importantly, the 90M terms as a vocabulary to describe imaging level metadata. So similar for the SNOMED CT vocabulary and the ReproSchema vocabulary. Difference between SNOMED CT and the other two is that there are also things that we're giving back to the community vocabulary. So for 90M terms, we have some additional things that we want to mention that are not yet in the 90M terms. So this is something that we're planning on adding back to 90M terms. For ReproSchema, the data sets that we're looking at in Parkinson's actually have a pretty extensive amount of assessment tools. And so we would like to describe them and also feed them back to ReproSchema or contribute them to ReproSchema, so that, you know, when we say this exists in the ReproSchema namespace, we're actually saying the truth. Excuse me. Then there are a number of data sets. So OpenEuro, as I've just shown, we have done a harmonization a one-off harmonization, but still, we would like to contribute these harmonizations back. But maybe more importantly, and what's shown here in purple, is that something we discussed last year is that it could be a really nice idea to have something like this annotation tool, not exactly like it, but the idea of it that can serve different use cases. So you can come in there and say, okay, I have a data set, I want to share it on Dandy or OpenEuro, and I want to generate a data dictionary for it and go through some of the required harmonization steps for this specific data repository. And so for this, it would be a really great way of working together. And then we've been in touch with DataLad. One idea here is, again, to find a way to use DataLad as something we can offer the people who have found a cohort and say, okay, well, if you go this way, you can actually get access to the data. But also through things like metadata lad and metadata extraction, we may be able to make DataLad aware of the type of annotations that somebody has done, for example, with the tool. And lastly, all this is kind of happening in the ReproNim cloud, and so the contribution here would be that we would obviously like to link this graph representation with other graphs that exist in the field. So, for example, the ReproNim graph stores like ReproLake. And there's some others that I'm not going to mention because I'm pretty sure I'm almost out of time. And so the next steps for us, so at the moment, we're still trying to finish the initial prototype to show what this idea of sample level cohort search could look like. But really the intention here is to go relatively quickly from that to making sure these tools and this infrastructure is useful for Parkinson researchers locally at the MNI. So there is the Quebec Parkinson Network that we're involved in trying to annotate in this way and make it findable, but also allow people in the community to find similar data sets. The other, and I think parallel next step for us is to really find out how we can work together with some of the other initiatives to not only find nicer ways of using the cohorts that have been found, but also thinking really about, well, how should this be done? What use cases are, the most important? And they may not necessarily be the ones that we picked here, but kind of using these initial prototypes as a way of showing, okay, this is something that is currently possible, and how can we turn it into something really useful? And then eventually, we would like to see this being useful for people outside of our local community, and also some other things that I haven't talked too much about is understanding how we can deal with things like clinical data at hospitals like the Douglas I'm working at, or the Enigma consortium we have had some conversations with. So yeah, that's essentially the overview, and that's the end of my slide. Thank you very much.
Great, thank you so much, Sebastian. That again is impressive and yeah, challenging to digest it all, and it's great to hear it. I'm always struck by these various trade-offs about, on the one hand, keeping things simple enough, and another thing, capturing enough detail to do something. And again, BIDS is sort of classic for the 80-20 problem. A solution that got 80% of the stuff, left the hard 20%. So then users use it and love it, and then you eventually run into, oh gee, I'd like to know something about the other stuff. Well, then NIDM comes in, for example, to that 20%. Well, it's hard to start with, so there's no easy part of that. But again, there's perhaps the easier 80% of that hard part than the next 20% of that. So no, I didn't know if there's anything you wanted to say on sort of how to balance easy across very complex, things. And then the other thing about easy, and again, I think what I love about some of the stuff as you've shown is easiness is not necessarily the model being easy, but the tools that make that complex model easy to use. So I just wanted to throw those concepts out there for more elaboration on your part.
And thanks for the question, because that's, I think, exactly what I wanted to talk about as well, because I think, so maybe the second question first. I agree, it's not about the model. And to my view, I mean, the people who are creating the data are researchers. If Schema.org already has a hard time convincing webmasters to learn really complex things, we're going to have a really hard time convincing researchers who do many other things of learning highly technical stuff. So they probably won't ever see this. They will interact with some way of annotating their data or using the tools. But I mean, I think there's still a lot of value to starting really simply, because I mean, you'll need to see what works in practice, I guess, and the best way to do that is to have people use it to some extent. And so I think for me, the takeaway from these two examples is that you can go complex first, but it's like what OMOP, I think, is an example of that. But I think that's just really at a scale that is not really easy to replicate. I mean, this is almost like a one-off type of initiative, and I think that an iterative approach is lets you better figure out what really works, and also maybe stop going down a direction that the people who eventually use this won't be as interested in. So one of the things that Schema.org has done repeatedly is also look at what concepts in the vocabulary are not used and then throw them out again. Like sometimes you run into a direction you don't like, but it's probably a good idea to figure this out by having something in people's hands, and then they tell you about it. I think that's how I would maybe answer that. Yeah.
The floor, of course, is open to others to ask questions out there. Anyone?
Hi.
Good.
Hi. I have a comment and a question. So thanks a lot for the overview, because I mean the problem is known if you're doing clinical research, is basically a problem you face, and everybody's stuck on their 2 or 3 data sets. So first, the simple, as you describe it, simple approach as you showed is really impressive. If that's formalized and available with the tool, I think that would help a lot of people directly, because everybody does that for one study, and even to use that again is it's most of the time difficult, and let's say the mistakes are the same most of the time. So that part will really benefit a lot of people, even if it's that simple as you show it. And I would even as well. Yeah, sorry. So that part I'm really looking forward. And I would even the schema and how you present it will help everybody who's trying this. But if you have an annotation tool with the complex, or first easy, but then vocabulary with it makes it even a lot richer, and that's what I like about it. So I would really care about the 80% easy part a lot more first, because the 20% and the rest is really difficult to generalize and to have right. And of course, an iterative way it was mentioned that way, but I would really say the first thing that's done right already, like it's that what will help everybody that's doing that stuff. And specifically, even if I have the 1 or 2 examples from a neuro that I can do as the replication analysis or test set and so on and so forth, that would be really, really cool. And I mean, the rest, as you pointed out, is really impressive. So I just want to say really cool, and I'm looking forward. And if there's anything to use, I would be happily to channel to Jülich where I work to people to give it in their hands to do the work they're doing anyway with that tool, and maybe give some feedback on that. So thanks.
Well, thanks a lot. I mean, I totally agree. And one thing I do want to say here is, I kind of glanced over this. There's a reason that this is a graph model, other than it is that it's really easy to rethink some aspects of the data model. So you can draw another edge if you find out that you don't only care about these 4 things, you know, and I think that is really something. I agree with it. It should be easy to iterate on it and add complexity as is needed. For example, we are already aware of that the people who we want to use these things will also want to know about derivative data, right? They want to know, has somebody actually processed this? Is this cohort, has somebody run this on fMRI Prep LTS, right? So this is something we can't represent, but it should be easy to add that and to do it in a way that is simple, but well done, I guess. Yeah. So
yeah, just to clarify, I think the annotation and that part to unify to get the graphs should be very easy, but what you get out of it could be a lot more complex under the hood or above. So absolutely agreed. It was not for me to be simple, but you know.
No, right. I totally agree with what you're saying. I think simple is good. But for example, this is something we talked about last year, and I think there's been some agreement as well that an annotation tool like this can be useful for a number of different places. So if you upload to OpenNeuro, as you said, BIDS makes specifications for the imaging side of things, but it leaves the demographics out, right? So you still have some heterogeneity on the participants' TSV file. So if it was possible to tell people, hey, when you're uploading your data, go through this relatively simple annotation process, and out comes not only the data dictionary that you want, but maybe also something a little bit more homogeneous, that might be helpful, right? So I think that would be something we could also think of doing together and contributing to these data curation centers.
I see that Keter.Dave has his hand there.
Thanks. Yeah. Thanks, Seb. This was super interesting. I love the build-up as well. That was like, you know, super informative for me and probably others to understand how schema.org fits in and so forth. But so I just wanted a comments, question kind of thing. You know, what I see that you did here that to me was very interesting, and I think you know, leaning on these RDF graph-based models, you know, facilitates is the idea that you're kind of creating a federated database, you know, using the graph structures and aligning on vocabularies and terminologies versus doing a federated, you know, relational database system where you know, have a human, you know, physically mapping across the database schemas. And so, you know, in a sense, this is, you know, even though it required, you know, quite a bit of your time to come up with this, probably ultimately far less time than would be required by, you know, going through each relational database schema at all these, you know, sites that contain Parkinson's data and kind of mapping them together. So that's just a comment. I think this is an interesting application of the graph structure, leaning on the ontologies and terminologies and getting to a place where it's, you know, presumably useful for investigators. And so if we could, you know, continue that in some way, you know, pushing on these models and, you know, such that we could annotate these graphs like you've done with additional information and not break the original graph structures so that the original libraries and, you know, tools work with them, that would be optimal. And then the second comment is kind of, you know, how do you see, so, you know, how do all these tools work together for a user? So, you know, can you foresee a place where regular users could go and say, I want to make a federated query tool, essentially using these graphs for my use case? And is there a route that you can envision that someone might be able to do that? Is it a, you know, I don't know. Do they have to become experts in RDF? Hopefully the answer is no, and that's where we'd like to get.
Yeah, I mean, I guess that I really like that question because I mean, there's a little bit dreamland, but I think that would be ideal because something that we've seen with Schema.org, and I just like glanced over it, they built it to essentially give you a flight search tool or something like that, right? You find flights from different websites, but you can now also find data sets. You know, it's the same graph. It has a different use. So I think that is part of what I find so appealing about this is because, sure, the tools are important to get the data in and make it convincing that it's useful, but in the end, if we do have this graph representation, then there might be ways of using this information that we didn't think of yet. So maybe somebody just wants to build a dashboard and say, what is the neuroimaging data that people know about or something? You could do that. More to your question, can you do that without learning RDF? Well, not at the moment. I guess that would be something we need to think about, but I think you should be able to. And similarly to how, you have how BIDS works, I think. BIDS is, BIDS has BIDS apps, BIDS has Python APIs, right? So you can use BIDS without being intimately familiar with its internal structure. And I think that's a great thing. And I don't know exactly what that would look like here, but I very much agree with your first point about clicking things together. This is also why I put interlex here, because even though for this demonstration, we chose to be very prescriptive in what vocabularies people should be using for the different domains that we're looking at, interlex could be a place where we resolve some of the relationships between different ontologies that may exist in other graphs. So we don't have to go and do all these mappings because, as you said, something like OMOP, where you have relational schema alignment, is not very fast, both to set up and also to run. If you run a cohort query on OMOP, they'll send you an email when it's finished. So it's not the same type of thing.
I'm going to turn the questioning over to Satra. I'm just going to insert into the record, because we're at the end of our hour, thanks to all the people who attended. We'll continue to record and keep on going, but in case people have to drop off, next month, Friday, March 4th, will be Pierre Herholtz and some machine learning excitement. So without further ado, Satra.
Thanks, Seb. This was very nice, and I'm going to steal some slides from you at some point in time. A couple of kind of questions, kind of picking up on where Felix left off with kind of the easy part of things. What do you think should be the strategic approach? Because this still requires a lot of work to be done. And between, targeting a set of people like Google did, they didn't target all the people consuming that data, they target the developers who could put that information in. And that's in rare supply in the neuroimaging kind of community space. So in the balance of where to leverage Felix's 80% comment, what are your thoughts on what the starting point should be for the community to contribute to something like this?
I'm not sure I fully understand your question. I'm going to answer it the way I think I understood it, and then you can see. I think that I didn't give, obviously, the whole picture of where data is. Data is in many more places than this. It can be on Zenodo and OSF and somebody's hard drive and so on. I think that the 80-20, from my perspective, are these DCC data repositories, because they already have either some form of existing structure that we can relate to. So, for example, the Dandy Archive, right, has an API, and there will be ways of using the representations of the data that are there. And also things like OpenNeuro that are less internally harmonized, I think, are still a good little bundling place for folks to use, where it might make sense to put some effort in. There's a lot of, if you looked at the demo, 90% of the data in there is from OpenNeuro, so maybe we should focus there because that seems to be where all the things are coming from. But I think it's less. I don't think it'll be as useful to try and make these tools for really individual researchers who just want to upload their data anywhere. I think it might make more sense to begin with the places that people are already kind of mandated by some of the upcoming research data management plans to put their data anyway, and figure out how we can talk to each other at that level. Is that what you meant with your question?
I think so. I think the balance here is still on that crowdsourceability, right? So from a Google scale, developers are a large resource. From
Yeah, I
a
see.
neuroimaging perspective scale, the DCCs are very small relative to the rest of the crowd. Is there something in between where one could help? It's almost like partly talking about a research software engineer space
Yeah.
of folks somewhere in between the individual users and the DCCs that can help, right?
I don't know. I think it's a really important question. And I think that's another takeaway from the two examples I tried to show is strategically, you should put the complexity with where the resources are. So that's why Google can harmonize data after the fact and OMOP, I guess, doesn't. But what that means for us, I'm not exactly sure. Maybe there's such a space, but the way I was thinking about it is if it's intuitive enough, then the most resources that exist, hopefully, are the actual researchers trying to share their data. So if we can ask them to do some of the more manual work, this might be easier. So something like an annotation tool that really doesn't annoy you, so you don't want to talk to anybody at the end of the day, I think would be a good thing to have. And then people might be willing to go through these steps and then also see the benefits through something like these tools. That it's kind of how I'm thinking about it.
I was selfishly hoping that you were going to get there, so
yeah.
I'll put a thumbs up for that.
Oh, he will. Just wait. His next month he'll give another talk. No. What I won't say tension, but on the one hand, lots of your examples, generated data from OpenNeuro, which is on the one hand good. And OpenNeuro is an interesting thing because it's a central data repository, but it's made up of lots and lots and lots and lots of fairly independently acquired stuff.
Yeah.
But there tend to be the mostly smaller-ish studies. In your particular Parkinson's example, probably the PPMI or the QPN or whatever are kind of your more interesting targets in a sense because they are larger, pools of that Parkinson's data. But but that's not a central, it's three central things. So again, it's just trade-off and balance between where the big pile of data that you're actually after is versus where they're stored. And so again, I think OpenNeuro is a nice example, but so are the big initiatives, such as those other data stores. Yeah. And again, I think Enigma is another one of these good sort of hybrid examples of lots of people with lots of little studies can make big studies, but you got to get through this harmonization, annotation stuff one way or another. Enigma's done a lot of that by hand, and man, the power of both learning from them and making their job easier, I think, is a good additional output of this.
Absolutely. And I think something that maybe I should emphasize more is the use case of figuring out whether a closed data set is worth your time before you go through the process is important. So the Douglas, again, is a mental health hospital where I work, and they have a lot of data that they don't really tell the world about because they couldn't share it. But people might be really interested to learn that the Douglas has one of the largest brain banks of donated brains in Canada, and all these things. You might not even have heard of the whole institute, but and exactly like you're saying, these big consortia, I think, are really very attractive to talk to in this context as well, because they often have some type of internal structure. OpenNeuro, I think, was in this case maybe even a little bit of a hard problem that we wanted to look at because there is so much variability, as you said. But yeah, with PPMI and QPN, those are data sets that people, I think, are really going to be interested in searching at a sample level, and they're also at a high curation and data quality level. So I agree.
Yeah. I know we're getting to the end of our official time. Are there any burning questions? Oh, Felix, get the last question.
Yeah, just a very quick comment. So for closed data sets, of course, it's difficult, but to get and to analyze. But if you're talking about annotations and looking at them with any kind of tools or analyzing annotations per se, so that could be very interesting to as well, getting data back from closed data sources, and basically have there an interaction which is only on the metadata level, going deeper. And I mean, Enigma is one of the examples where you can do it there and only channel back a few things. And I think that's very important and should be targeted as well. And in the end, it's the easy as well on how to get the data as well. And it's a very hard problem, as Sada put forward, that to get people actually using this, because you have a lot to do. So it's really the ease of use and the direct profit of how do it this way and not another way. So that's, I think, are the how I say, the sweets to give to people to channel back the data.
Yeah,
right?
I agree. Thanks for the comment. I think that's really interesting. But, so I think what you're mentioning there is almost like a federated analysis type of idea, right? Yeah.
Yeah. Okay, well, thank you all for attending and all the questions. And of course, this dialogue can continue in ether space, email, Twitter, other venues. Throw the little clappy emojis on. And I'd like to thank you one more time, Sebastian, for joining us. See you all in the web or next month at the March 4th webinar with Pierre Herholtz. So I'll officially call today's session to an end.
Thanks for having me. It's fun.